Hello, welcome to Lecture 2. Today we're going to begin to talk about our general physics concepts. Over the course of this lecture, we're going to look at solving problems using the units of motion. We're going to look at solving problems with one-dimensional motion and solving problems that involve free fall. Our study of motion will be focused on the location and movement of our object of interest. Our goal here is to try to provide numerical values that can answer questions like the following. We will want to know where our object is in space. And to do this, we use the concepts of position and distance. We will also want to know how the location of our object changes. This describes the speed or velocity of our object. Our objects don't always move consistently, so we'll also be concerned with how the motion of our object changes over time. Our speed and velocity can be constant or non-constant. Another thing that non-constant says is that the object has acceleration. To support these concepts, we will also need to have an understanding of terms like scalar, vector, average, and instantaneous. Scalar values are values that have magnitude only, so it's just a number. Vectors are quantities that have magnitude and direction. When we're talking about vectors, we have certain conventions we follow. Directions usually have pairs, so you can go left or right. Similarly, you can be moving down or up, west or east. And when we want to do calculations that involve direction, we apply the convention that left, down, and west are negative values, and right, up, or east are positive values. Every time we're talking about how objects move, we could be talking about two different types of measurements. An average measurement, and our average measurement always compares the initial and final conditions to the amount of time it took for that change, whereas the instantaneous measurements will look at the smallest possible snapshot of time. Your textbook mentions the concept of looking at these values when the limit of time approaches zero. This is a calculus concept and it's often used in physics calculations, but it will not be used in this course. Let's look at this concept of where our object is in a little more detail. To know where an object is, we need to develop a system for assessing a numerical value to its location. There are two concepts that deal with these types of questions: position and displacement. Position is represented with an X that has a little vector arrow over top. This should signify to you that position is a vector quantity. When we're talking about position, we will measure our position back to an origin. To better understand this concept, let's look at two examples. We're going to find the position of the orange dot and the purple dot. We can represent the position of the orange dot as 2 to the right of our origin. The origin is typically represented as 0 on any of our axes. Similarly, we could represent the position of the purple dot as 1 to the left of the origin. The other concept that we use when we are talking about position is displacement. Displacement is the change in position of an object. We represent displacement with this symbol. This triangle is the Greek letter delta, and we use delta to stand for change in. In our example, we could calculate the displacement between the purple and orange dots. We need to apply the convention we mentioned earlier in order to be able to do calculations with vector quantities. Because we can't do math with right and left, we need to register those directions as positive and negative. So our orange dot would be +2, and our purple dot would be -1. If we sub these values into our equation, we see that the displacement between the orange and purple dots is -3, which we would interpret as 3 to the left. The convention here is stating that we ended at the purple dot and started at the orange dot. So every time we calculate a change in, we calculate it as the final position, so where we are, minus the initial position. Let's look at this concept of where our object is in a little more detail. To know where an object is, we need to develop a system for assessing a numerical value to its location. There are two concepts that deal with these types of questions: position and displacement. Position is represented as an x with a small vector over top. This should signify to you that position is a vector quantity. When we measure position, we will always measure with reference to an origin. To better understand this concept, let's look at two examples. We're going to find the position of the orange dot and the purple dot. We can represent the position of the orange dot as 2 to the right of the origin. The origin is typically represented as 0 on any number line. Also, we could represent the purple dot as 1 to the left of the origin. The other concept that we use when we are talking about position is displacement. Displacement is the change in position of an object. We represent displacement with this symbol. This triangle is the Greek letter delta, and we use delta to stand for change in. In our example, we could calculate the displacement between the purple and orange dots. We need to apply the convention we mentioned earlier in order to be able to do calculations with vector quantities. Because we can't do math with right and left, we need to register those directions as positive and negative. So our orange dot would be +2, and our purple dot would be -1. If we sub these values into our equation, we see that the displacement between the orange and purple dots is -3, which we would interpret as 3 to the left. The convention here is stating that we ended at the purple dot and started at the orange dot. So every time we calculate a change in, we calculate it as the final position, so where we are, minus the initial position. The next thing we need to talk about is how has our location changed? To attribute a numerical value for how a location is changing, we need to introduce the concept of motion. The difference between the two ways that we talk about motion will rely on your understanding of scalars, vectors, average, and instantaneous. The first way that we talk about motion is our speed, our change in position over time. Speed, represented with the symbol v, is a scalar quantity. Remember, this means that when we talk about speed, we will talk about magnitude, but not direction. The other way we refer to motion is to think about velocity. We represent velocity with the symbol v with a small arrow over top. Again, this should let you know that velocity is thought of as a vector. This means velocity has both magnitude and direction. When we solve problems in this course, this is almost always the version of motion that we will be concerned with. One of the common misconceptions we experience is that students often accidentally refer to speed when what they really mean is velocity. To calculate velocity, we will use the formula that velocity is equal to the change in position over the change in time. There are two ways we can look at velocity. We can calculate the average velocity, which is calculated using the initial and final positions of an object. And this assumes a roughly constant velocity, meaning that it will give us a result that assumed the vehicle traveled at the same velocity through the entire time frame. The other form velocity takes is the instantaneous velocity. Remember, instantaneous means that we're looking at a very small snapshot of time. While it is possible to calculate this value using a little bit of calculus, we will not be calculating that way. When we think of instantaneous velocity, a speedometer would be giving us the magnitude of a velocity at any snapshot in time. There are two types of problems that we will see with instantaneous velocity. We can be provided the instantaneous velocity, or we can try to predict the instantaneous velocity. And either of these will correspond with a specific point in time. When we talk about objects that are in motion, the motion of our objects can be non-consistent, meaning that we have to have a way to measure how much the motion changes. To quantify that, we talk about acceleration. Acceleration can be considered as both a vector and a scalar. We represent acceleration with an A with a vector arrow over top, and we calculate it as the change in velocity over the change in time. It's important to take a moment to consider the dimensions of acceleration. Because acceleration is calculated as the change in velocity over the change in time, it will have units of meters per second divided by seconds, which we simplify to meters per second or meters per second squared. This is telling us that every second that passes, our meters per second changes. Acceleration is a vector quantity often, and this leads to one of the major misconceptions. Negative acceleration does not always mean slowing down. Negative acceleration means more negative velocity each second, and positive acceleration means more positive velocity every second. So if we consider pairings of velocities and accelerations, we can have 4 different results. If we have a negative velocity with a negative acceleration, that means we can consider an object that is moving left and getting faster. If we have an object with negative velocity and positive acceleration, the object can be considered still as moving left. This time it is getting slower. And we'll move this out of the way to make room for the last 2 pairings. An object whose velocity is positive and acceleration is negative is an object that's moving right and getting slower. Finally, an object with a positive velocity and a positive acceleration is an object that's moving right and getting faster. It's very important for you to consider each of these 4 possible pairings of velocity and acceleration as they drastically change our calculations. I'm going to clear those pairings out to talk about free fall problems. Free fall problems are a special case of motion, and they're a type of problem we often solve. To solve free fall motion problems, we make several assumptions. The objects are falling freely, they are near Earth, and we ignore air resistance. With all of those assumptions, we have a known acceleration. In these problems, we will look at the acceleration due to gravity, represented by g with a vector arrow, and that acceleration is known to be 9.8 meters per second squared in the down direction. As we move forward, when you see a problem that states it's a free fall problem, this means you can make the assumption that you know the acceleration. Now that we have an understanding of those physics concepts, let's begin to solve some calculation problems. Using the data in the table below, calculate the average acceleration of the vehicle during the requested time intervals. You'll see that the table gives us certain times, the instantaneous magnitude of velocity for that specific period in time, and the direction to go with each of those magnitudes of velocity. I'm going to walk you through part I and part 3, and I'll leave parts 2 and 4 for you to follow along without audio. To calculate the average acceleration, we need to calculate the change in velocity over the change in time. Every time you see that change in formula, you are going to take the value at the end of the time frame and subtract it from the value at the beginning of the time frame. So the change in velocity is the final velocity minus the initial velocity. And the change in time is the final time minus the initial time. Let's focus in on part I. To start any problem, we need to identify our given values. So if we're looking at the time interval from 0 seconds to 1.50 seconds, we need to identify which is our final and which is our initial times. Our time at the end of the interval is 1.5 seconds. And our time at the beginning of the interval would be 0 seconds. Similarly, our velocity at the end of the interval is equal to 10.60 meters per second east. Our velocity at the beginning of the interval is 0 meters per second. In order to calculate the average velocity, we need to assign one of our directions to positive and one of our directions to negative. By convention, I choose east to be positive. Note, somewhere on your solution, you should mention this denotion. Now, stating our formula that we wish to use and substituting our values in the correct order, our calculator will tell us that this is 7.0 and 6 repeated meters per second or meters per second squared. If we consider our significant digits, then this is approximately 7.07 meters per second squared east. We know the value is in the eastern direction because the answer to our calculation was positive. A statement here would follow along the lines of the average acceleration between times 0 and 1.5 seconds was 7.07 meters per second squared east. I'm going to let you guys work through part 2, but here's the solution. And I'm going to work through part 3 and highlight some of the differences between it and part 1. Again, we're going to list all of our values with time I initial being 2.7 seconds and time final being 4.3 seconds.
And the velocity of the vehicle at 2.7 seconds is our initial velocity, and that's 5.2 meters per second east, so it has a positive value. Our final velocity is 1.20 meters per second west. So in order to do our calculation, this velocity takes a negative value. So when we select our equation and input our values, it's very important that you keep track of that negative sign that comes with the final velocity. Here we have a west velocity, and when we subtract it, the velocity has a more negative change. So we see that our acceleration is minus 4 meters per second squared, which is approximately 4.00 meters per second squared west. Some things to take notice. Well, in both part 2 and part 3, the vehicle was accelerating to the west. In part 2, that meant that the vehicle was slowing down as it was still traveling east. But in part 3, the vehicle went from traveling east to traveling west. So it slowed down to 0 meters per second velocity and then began accelerating in the western direction up to a speed of 1.20 meters per second. I'm going to leave you guys to do part 4, but note you have to be careful with the way you set up your negative signs here, as the vehicle now begins to slow down. So it has an acceleration in the easterly direction while traveling west.
Throughout our course, we will solve more problems than just acceleration problems. There are several relationships between velocity, position, acceleration, and time that we are able to create equations for. We use these equations to make things measurable that we don't have access to. Again, this can be so that we can calculate back to a previous value or predict out to a future time. As you look at these equations, they all share the same definition for their variables. Delta x is used to represent displacement, and while this does not have a vector arrow above it, it is very important to consider which direction would be positive as you complete these calculations. V subscript f and V subscript I represent the final velocity and the initial velocity, and you choose those 2 points based on your time frame of interest. A represents the acceleration for the time frame of interest, and T represents the elapsed time. Students need to be careful, as T is often going to need to be calculated as a change in time, even though the equations only represent the variable itself. One of the key assumptions made with these equations of motion is that the acceleration is constant through the entire time frame. If your acceleration changes in the problem, then you must repeat the step we did in the previous example, where we break the whole problem up into time sections where the acceleration is assumed to be constant. As you look at these equations, sometimes it helps to consider what each equation is telling you. The equation on the left can give you an idea of how fast you are going depending on how fast you are moving at the start and how long you spent accelerating or changing your velocity. In the second equation, we can see that how far you go depends on the amount of ground you cover from your initial velocity, as well as the additional ground you cover based on the amount you accelerated while moving. For the third equation, it's actually quite difficult to tell a relevant story because we don't have a solid perception of what a squared velocity would represent. But you can note that this equation is quite useful when you don't have a time measurement. And in the final equation,
we can see that the amount of ground we cover is based on our initial and final velocities and how long we were traveling. If you look closely at this formula, the highlighted portion is the way we calculate your average velocity over a time frame. Your textbook goes through the derivation of each of these formulas. I won't expect you to be able to reproduce those steps. However, you should review that portion of the reading, as the steps they use can come in handy when you try to solve a problem. With these equations, there are two key factors that we want to think about when it comes to solving problems that involve motion. The first thing you need to remember is that any equation can be rearranged using algebra. And the second thing to know is that any equation with only one unknown can be evaluated, which is the math way of saying you can plug in the known values and end up with one number that represents the unknown value. As you start to begin to sort out your strategy for solving any problem, use point 2 to let you choose which equations you want to apply to the problem. And when you have an equation that has two unknowns, use both of these points in combination to rearrange one equation and substitute it into the other, giving you one equation with one unknown. Let's take some time to work through a few examples. The first motion example, from time equals 0 seconds to time equals 4.15 seconds. The acceleration of the train is 0 meters per second squared. At time equal to 4.15 seconds, the train is at position 10.3 meters right. And then the train travels until 5.34 seconds with an acceleration of 1.22 meters per second squared. What is the final velocity of the train? For problems like this, you will likely have to read the problem at least 2 times. The first time you read the problem is to get an idea of what's going on, and the second time is to begin to pick out some of the key points. We should note here that the acceleration in the first time chunk is 0, which means the train has a constant velocity. But in the second time chunk, the train has acceleration. For all of our motion equations, acceleration needs to be constant. The change in acceleration here tells us that we need to split this up into 2 time frames. For difficult problems, it often helps to draw a diagram sorting out some of the given information. So first, I break up the problem into the 2 time frames. And then we add that 10.3 meters is covered in the first time frame. We'll use the symbol delta x with the subscript 0, 1 to represent the distance traveled between time 0 and time 1. The other piece of information we're given is the acceleration from time 1 to time 2. And remember, we were asked to solve for the final velocity of the train. Now we need to go back and look at our equations of motion and try to determine which equation is useful. From the last slide, remember, we're trying to choose an equation here where only one piece of information is unknown. If I look at the 3 spots that velocity final is mentioned, in the first instance, our velocity initial is unknown, but we know our acceleration and we can calculate our time. In the second instance, again, velocity initial is unknown, but we know the acceleration, and perhaps we could calculate the change in position. But to do that, we would need velocity initial as well. And the same problem happens in the final version.
So let's start by looking at the first instance. So I choose the equation I want to use, and I'm going to modify it to fit the notation that I'm using in my problem. So my velocity at time 2 will equal my velocity at time 1 plus my acceleration between times 1 and 2 multiplied by my time difference between times 1 and 2. I'm going to look at my given information and see if it's possible for me to find out what my velocity is at time 1. At time 1, I've been traveling a given amount of distance in a known amount of time. And remember, I was told my acceleration was 0 meters per second squared. So if I can calculate my average velocity in that time frame, I will know my velocity at this point in time. So let's make that substitution into our formula. You should be comfortable using the average velocity formula wherever it's required, even though it's not one of the 4 equations mentioned on the left side of the screen. The time interval from time 0 to time 1 is just the time at time 1, and this is because time 0 is 0 seconds. For calculations as trivial as this one, it is okay to just substitute the value. But for the time elapsed between time 1 and time 2, we will need to substitute both values and calculate the change in time. I encourage you to practice with your calculator so that you can enter this entire calculation in one step. Remember, every time you complete a calculation, it increases your chance for error and introduces a rounding. Often, the calculator rounds at 9 digits, which is far more than we're going to keep, so it is possible to avoid these errors. But when we deal with really large and really small values, it is possible for a rounding error to creep into our result. Our calculator is good at calculator things and tells us that we get a final velocity of 3.933727711. Now it's time to consider our input values and significant digits. With the exception of the zeros, all other values were given with 3 significant digits. It is safe to assume here that our answer should include 3 significant digits. And we can state that the train's velocity at time 5.34 seconds is approximately 3.93 meters per second right. This problem should identify to you that not all problems can be solved in one step. And it should highlight a strategy that you can break a difficult problem up into 2 pieces and use 2 equations to solve for the final answer. Let's look at a slightly more difficult problem. So this beautiful old jalopy is able to brake at a maximum acceleration of negative 1.8 meters per second squared. Is the car going to be able to stop before the sign? So we need to make sure that we pull out the important information and decide what is the question asking us. We know that the velocity that the car starts with is 12 meters per second, and that is currently 36 meters away from the sign. So we're given velocity initial is equal to 12 meters per second. Our intended change in position should be 36 meters. And our acceleration is given to us at negative 1.8 meters per second squared. If we're being asked, is the car going to stop before the sign, then we need to use the information we have and determine the final velocity when the car reaches the sign. Looking at our equations of motion, we see one equation that mentions final velocity, initial velocity, acceleration, and change in position. So let's start with that equation. The equation begins arranged for velocity final squared. So we must manipulate the equation to be for velocity final. And I hope you're comfortable taking the square root of both sides to accomplish this. In this problem, after using one equation, we only have one unknown value, and we've isolated for that, so we can begin to substitute our values. And again, be sure you're practicing with your calculator so that you can easily, in one step, get to the answer 3.794733192 with units of meters per second. Looking at all of our given information, that means we can say that our final velocity is approximately 3.8 meters per second. Always remember, answer the question you were asked. Is the car going to be able to stop before the sign? Because we found that when the car reaches the sign, it still has velocity, then we know it is not stopped. We were expecting to see a velocity equal to 0 meters per second. So our final statement needs to address that point. When solving physics problems, you might want to keep in mind that there is more than one method for solving any problem. An alternate approach to this one could have been to assume the final velocity equals 0 and then solve for the required acceleration. In that case, finding that the required acceleration would be negative 2 meters per second squared would tell you that the car was not able to brake hard enough to stop before the sign. There's an entire class of problem that we mentioned already. Free fall problems. Remember, free fall problems come with several assumptions. While making eggs, one egg rolled off my 92 centimeter tall counter. How many seconds did I get to spend in sheer terror as the egg plummeted towards the floor? We still use the same method to solve this problem. We have to evaluate the information we've been given. We have a distance given to us, 92 centimeters. We can use this as our displacement. Because the value is given to us in centimeters, and we need to work in meters, you need to make a conversion. The other thing to consider is that the egg falls from the top of the counter towards the ground, which means it has a negative displacement as it works its way down. The problem doesn't give us much other information, but we know it's falling, so that lets us assume the acceleration is equal to the acceleration due to gravity, which is 9.8 meters per second squared down, so we list that as negative as well. We're asked to find time, so this is our unknown. If we look at our equations of motion, one equation that seems promising is the displacement is equal to the initial velocity times time plus 1/2 of the acceleration times time squared. You may notice that the problem does not mention an initial velocity. Let's take a second to consider our scenario. If we have a counter and the egg rolls off the edge, the instant the egg leaves the counter, it hasn't started falling yet. So until the egg is off the counter, its initial vertical velocity is equal to 0, and then it begins to accelerate. So we can use that to simplify this equation of motion. If our initial velocity in the vertical direction is 0, then even when you multiply it by any amount of time, it will still be 0. Now we have an equation we can use. We just need to isolate t. Using some algebra, we should find that time is equal to the square root of 2 times the displacement divided by the acceleration. With one equation and one unknown variable, we can begin to substitute our known values. It's worth pausing to note here that if we didn't correctly set up our positive and negative directions, there's a risk that only one of these values would be negative. If only one of these values had a negative sign, then the entire fraction underneath the radical
would be negative, and you cannot take the negative, and you cannot take the square root of a negative value and get a real answer. Plugging this into our calculator, we will get the value 0.433307168. Evaluating our significant digits, we see that the egg takes approximately 0.43 seconds to reach the floor. Our units are seconds because we have meters divided by meters, which will cancel each other out. And then we're dividing by seconds squared, which should bring those units up top, and taking the square root of a squared unit will result in a linear unit. And our final statement is the 0.43 seconds the egg took to reach the floor felt like 3 minutes. You should be starting to see that sometimes the difficult portion of a problem is not the calculation, but that almost all the work is done in just setting the problem up by knowing which equation to choose and rearrange, and also which assumptions you can make. There's another special case of motion problems that involve falling objects that were launched with an initial velocity. This type of problem is called projectile motion. For this week, we are only going to look at problems where the motion is strictly up and down, so there'll be no horizontal projectile motions. We leave that for 2D motion next week. When solving this type of problem, we have to make some more assumptions. First, the projectiles are ballistic. That means that their motion in the air depends entirely on their initial velocity, and they have no other propulsion. When projectiles are in flight, we know something about their horizontal motion, which will always be referred to as the x direction. We will know that the acceleration in the x direction is equal to 0. This tells us that the velocity in the x direction is constant. And for this week, that means it's 0. Now let's look at what we can tell about the vertical direction, which we denote with y. Just like in free fall, the acceleration in the y direction will be equal to the acceleration due to gravity, which is 9.8 meters per second squared. An interesting characteristic of ballistic projectiles is that the velocity while the projectile is rising is equal in magnitude but opposite in direction to the velocity while the projectile is falling for any given height, and that the vertical velocity at the projectile's maximum height is equal to 0. Let's look at these assumptions in action. Picture an object, and let's launch that object with a velocity of 2 meters per second. It's going to move up and up and up and slow down to 1 meter per second until finally reaching its max height where it's got a velocity of 0 meters per second. Before it begins to fall and accelerate, getting to -1 meter per second and -2 meters per second on the way back down. The way we know where the max height of the object is because there is no more upward velocity. Also see how the velocities are equal and opposite at each given height. Let's revisit my doomed egg. As I recall it, I did not actually just watch in awe as the egg fell to the ground. As it rolled off the counter, I reached out and tried to catch the egg. But I bobbled it, and it seems like all that managed to do was throw it up into the air until it reached a height of about 1.19 meters. Of course, I'm just estimating. The question I'm going to leave to you is, why would I have been better off to just let the egg fall? I want to add a portion here. I want you to check your understanding of dimensional analysis. Units play a pivotal part in our understanding of motion. When we rearrange our equations of motion, we can use dimensional analysis to do a quick mental check that we have correctly completed the rearranging. You saw us do this on the first free fall problem. So think of this. Knowing that you covered 13 meters at a speed of 5 meters per second, how long were you traveling? We're given displacement and speed and asked for time. The equation of motion we have is that velocity or speed is equal to the distance traveled over time. For this level of equation, I'm sure most of you are comfortable rearranging to time is equal to change in position over velocity. But it's possible that some of you got the order of rearranging confused and tried the incorrect rearrangement of time is equal to velocity multiplied by change in position, or you may have tried time is equal to velocity divided by displacement. A quick analysis of the units would have helped us determine whether or not we made a correct rearrangement. So if we look at the first version, we have the units of meters from our distance traveled divided by the units of meters per second. Remember, when dividing whole numbers and fractions, that means we would have meters over 1, and when you divide by a fraction, you multiply by the reciprocal of the second fraction, so that gives us seconds over minutes, and this allows us to cancel out meters and meters, so that we're only left with seconds as our unit. Let's look at the first incorrect rearrangement. From velocity, we have meters per second, and from displacement, we have meters. When you multiply these together, we end up with meters squared per second, and we cannot measure time in those units. In the third rearrangement, we have meters per second divided by meters, which means we're going to have to take the reciprocal of meters, which gives us meters per second times 1 over meters, which simplifies to 1 divided by seconds, which is seconds raised to the negative 1. And again, this is not the correct units for time. I'm leaving you with an additional think about this problem. So on top of thinking about my doomed egg, I want you to consider that the typical F-150 pickup truck can come to a complete stop from 50 kilometers per hour in approximately 10.9 meters. Assuming braking is constant, how far will the truck travel under braking to complete a full stop from 70 kilometers per hour? Things you need to think of here are unit conversions, how to break this up into 2 parts, which equation to use, and finally, remember to answer the question that you're asked. This brings us to the conclusion of Lecture 2. In lab this week, you write your first quiz. Make sure you arrive to lab prepared to write. You'll need blank paper, a writing utensil, and a calculator. As mentioned in workshops, you could be asked questions from both Lecture 1 and Lecture 2. You do not need to memorize the equations introduced in this lecture. I will provide them to you on any quiz and any test. During class, our focus after the quiz will be Workshop 2, so you should print that to bring to the in-person class. And don't forget, you need to complete the Workshop 1 quiz before you come to that class. With this information, you should be able to work through assignment number 1. Because of the confusion with the textbook, I'm extending assignment number 1 by 1 week, so it's now due February 8th at 8 in the morning. This will not push back assignment 2, so you will need to start working on that a little sooner than normal. Have a good couple of days, and we'll see you in class.